welcome to Tuesday's edition of Cracking the Cryptic, where today we're going to be looking at this very intriguing looking puzzle, which to me looked like a Christmas tree, but it's actually called Diamond, and it's by zetamath. So, I mean, we need to say no more in terms of the likely quality of this one. It's got an enormous rating on Logic Masters Germany and an intriguing rule set. I just read the rules before I turned on the webcam, and yeah, they are very interesting indeed. I can safely say I have never done a puzzle with these rules before. But before I read them to you, a couple of things to mention. Firstly, I want to say a very happy birthday today to Roy Whitelock down there in Melbourne, Australia, a place where I've spent many very happy weeks, especially down on the Mornington Peninsula where I have relatives. So Roy, I hope you have a super day. And now, what else to mention? Bubba is you. Now, our second attempt at playing this game is happening tonight at 10 o'clock UK time, so we're going to be live streaming our go at it. That'll be Mark and me together. We would love to have your company, so please do join us. Hopefully, if you're a subscriber to the channel, you already know about this because you should have had a notification. And speaking of Mark and me doing things together, we released yesterday our 400,000 subscriber bonus video where we answered community questions. We had a lot of fun answering those questions, and we've been delighted actually with the feedback. So do check that out. It's about an hour long, so allow yourself some time, but it's sort of like a podcast on steroids. Anything else to mention? Check out yesterday's video actually if you've not had a look at that puzzle by, I'm going to get the name wrong, but I think it's you pronounce it Nahelian. A new author to the channel has come up with this sort of extraordinary miracle type Sudoku. I think a lot of you would enjoy it. It is sort of approachable. It took me about half an hour to solve, I guess, but it's a brilliant puzzle, and the plaudits it's been getting are special indeed. So have a go at it if you have the time. And the only other thing to mention is for our patrons. If you're a patron of the channel on Patreon, thank you so much. Your support keeps the channel going. And there has been a fairly incredible reward for patrons, as at the start of October, this Lockout Lines puzzle hunt. The feedback we've been getting on it is stellar, although I will say that some of the later puzzles are very, very challenging indeed. So check it out. You will like it. Right, let's get on with Diamond, and I will read you the rules. We have got normal Sudoku rules apply. The digits on each line sum to the sum of the digits in the circles on the line's ends. E.g., if two circles contained 7 and 9, we can actually do that with this one, look, because it says, the example says, if two circles contain 7 and 9, let's put 7 and 9 into these places, and they are connected by a line of length 3, well, that's a line of length 3. That line might contain the digits 6, 3 and 7. Because, I suppose, 9 plus 7 is 16, and 6 plus 3 plus 7 is 16. So that's how it works. Basically, we've got to make the lines add up to the two ends of the line when you add them together. So it's like double arrow Sudoku in a strange way. Digits can repeat along a line and its circles if allowed by other rules. Okay, well, we just saw that there. There was I think one of the circles was 7, and then there was a 7 in the 6, 3, 7 combo. But let's just take a look at that and see. Oh yeah, so I suppose, I was just thinking, could you have like, could I put double 5? Oh, I didn't want to highlight that one. Could I just have 2 5s? So it's not like between lines at all. You can absolutely have two of the same digit at either end of a line. What you couldn't do in this example, though, is put double 5 here. That really won't work. But providing these two squares add up to 10, you can have the same digit at the end of lines. Right, so I've no idea how to do this. Do have a go yourselves. The way to play is to click the link under the video, as usual. Now I get to play. Let's get cracking. Oh, hang on. Is this the diamond? I've just seen that this sort of shape here, that looks more like a diamond than the Christmas tree. Oh, I don't know. You guys can tell me. Right, how do we start this puzzle? We've got given digits today, a 4 and a 5. Thank you very much, zetamath. Oh, and actually, thank you very much, zetamath's husband as well, who's going to be hopefully moderating the Bubba Is You stream later. Tristan is very, very good at moderating, thank goodness. What is it? Is it this row? At least we know some of the maths of this row, I suppose. I can't see anything else. I'm just going to have a look at this row. So this row, obviously it will contain all of the digits 1 to 9 once each. So it sums to 45. That's the secret. We only tell that to special people. So this row adds up to 45. What does that mean? Does that mean I can work out the value of this digit? So hang on, this row adds up to 45. That is, it's sort of double the sum of these. Oh, this is weird. Okay, so these two digits, obviously, they are the sum of those 3 cells, because that's how the rules work. So if I want to sum those 5 digits, I have to double this square and double this square to do that. Let's just, I mean, that must be right, because if this is a 7 and a 9, from the example, we now know these 3 squares add to 16, these add to 16, so in effect, these 5 squares are doubling these 2 squares. And then these 4 squares, which would be the end of the line, are going to be, these 3 squares are the sum of those 2 squares. Yeah, okay. So, yes, so this is odd, is what I've learned from all this. This is quite cunning, actually, and quite interesting. So let's just think about this and do it slowly. Those 3 squares are the sum of these 2 squares. So again, the sum of the first 5 cells in row 6 is double these 2 squares. Let's just highlight that. Double these 2 is the sum of the first 5. How do we sum the final 4? Well, those 3 are the sum of these 2. So now this has been tripled. This has just been introduced once, but now the sum of this cell on its own makes it a double square, so that acquires the rank of being purple. So purple with a blue flash is 3 times, purple on its own is 2 times, so this row could be represented as 2 times these squares, 3 times plus 3 times this square. And the whole row adds to 45, which is an odd number. That's going to double that is an even number, double that is an even number. So we need an odd number. So we're going to have this square as an odd number, because if we 3 times an even number, it's still an even number. So this is odd, is what we've learnt, and therefore it's 1, 3, 5, 7, or 9. Now, what does that mean? Does that put pressure on? Oh, I suppose all of these 3 are in the same row. This is weird because it's not like arrow Sudoku. In arrow Sudoku, these 3 squares would be low digits compared to the circle, but here these are axiomatically higher than this digit, and possibly a lot higher depending on the value of these 3 squares. Hang on, let me just think about this. If this is a really high digit, then that's impossible. That's absolutely impossible, because these have to be higher. That's, of course, that must be the case. So probably this can't be a 7 either. If this is a 7, now these 3 squares all have to be higher than 7, because even if I minimize these with 1, 2, and 3, one of them is going to have to be a 10. Ah, right, I'm starting to get my head around this. Okay, so this is down to 1, 3, or 5. If it's 5... no, that would work. We could fill these with some combination of 1, 2, 3, and 4, and these could be some combination of 6, 7, 8, and 9. Bobbins. What about if this is low? If this is low, there's hardly any pressure on those 3 digits, because effectively all we're doing is adding 1 to whatever those digits are. So we're giving ourselves maximum flexibility if this is 1. What about if this is 1 for the row? If this is 1 for the row, Oh. Oh, that's really clever. That's really, really clever. This is a 5, isn't it? Right. Just doing the maths on 3. I think this is a 5. Wow. Okay. This is smart stuff. Okay, let's look at why this is not 1. Well, the value we could put into the circles at the end, we could max these out with 8 and 9. That's 17. Now remember that the way we were expressing the 45 that we know that this row adds up to is 2 lots of these squares and 3 lots of this square. So if these two together add up to 17, 2 lots of 17 is 34. So this square needs to pick up the balance. 3 times this square needs to equal at least 11. Well, 1 and 3 don't work, because 1 times 3 is 3 and 3 times 3 is 9. Neither of those is equal to 11. So I think this has to be 5, which means these definitely are not an 8-9 pair, because if they were an 8-9 pair, that would then take us too high. Yeah, we know 3 times this is 15, so these have to sum to 45 minus 15, which is 30, divided by 2, which is 15, so we get a bit of a restriction. These have to be 6, 7s, 8s and 9s. This is either a 6-9 pair or a 7-8 pair. What a weird rule. Now these are quite high now. They have to be higher than 5. So these squares are 6, 7s, 8s and 9s. And these 3 squares are 1s, 2s, 3s and 4s. So just wondering about this square now, but I don't actually think that is very restricted. Even if this was 6 and 1, this would have to add up to 7. That's very possible. If it's 9 and 4, they have to add up to 13. There's almost no restriction on these dominoes. This line has to contain some low digits though, because these, hang on. In fact, that's not a 4, I've just noticed there's a 4 in that column as well. But look at these 2 squares. The maximum value of those 2 squares is 7. So the maximum value of these 3 squares is 7. So there must be a 1 and a 2 in this triple. And it must be... So this is either 1, 2, 3 adding to 6, which can't be double 3, because that would repeat 3 in column row 4. It's either... So if this is 1, 2, 3, this has to be 4 and 2. If this is 1, 2, 4, this has to be 4 and 3. So this square is always 4. That's probably why this given 4 is here. And this square is not 1 ever, because this is either adding up to 6 or 7. But we can't rule 4 out from this line, because that's not the rules. In fact, we're explicitly told 4 can be on this line, so probably is. That's not 4 anymore. So if that's not 4, that can't be 9. Oh, and if this... why does my brain work in this maddening way? Why, when I put this in, don't I immediately just write 9 in here? It's because I am doolally. Okay, because 4 plus 5 is 9. So by the rules of the puzzle... Oh, I thought I'd broken this one, but I haven't, of course. This is so counterintuitive. I'm so used to sort of normal arrows rules that I'm really struggling to get my head around this. 5 now has to be on a line in this box. That's probably not very interesting. So if that's... we can rule 6 out from this square, because this can't be a 1. There we go. So this is 7 or 8. This is 6, 7 or 8. Yes, and that does actually work with the mathematics of those 2 dominoes, or this domino here. There's definitely a 1 and a 2 in here. So is this square restricted? No, because the 1 and 2 only see that. So whatever that is, this domino is adding up to that plus 4. Ah, those two squares are the restricted ones. Oh, this is so peculiar, but I think that's true. Because we can't put 1s and 2s in here, and we can only put 1 of 3 and 4 in here. Oh, yes, in fact, that's it. That's it, right. You can't have 3 on this line. Because if you do, if this is a 1, 2, 3 triple, what digits are we going to put in these squares? Well, the minimum we'd have to choose from would be 4, 5, and 6, and there's no way of arranging those to ensure that we don't have to put a double-digit number in one of these squares. I can put a 4 and a 5 one way round, and that will require a 9 here, but then this square needs to be a 6, and whatever I add to the 6 in this circle is definitely a double-digit number. That's really clever and very counterintuitive. So this doesn't have a 3 on it. So now we know this is 1, 2, 4. And these probably have to be 3, 5, and 6, do they? We know one of them must be a 3. And it's probably the one that has to share its... The 3 probably has to share itself, because otherwise we're going to get a double-digit total, aren't we? Because if the 3 was here, these two digits are definitely higher than 5. They're at least 5, so they're definitely adding to a double-digit number. So the 3 goes at the top. These two squares now have to be 5 and 6. It's the only way that'll work, to make sure these two squares are an 8, 9 pair. We've got a 9 here, so we learn a bit more. That's 8, that's 9. This square here's a 7. This 3 is ruling a 3 out from this square. So that means that one's not 8, and it's not 7, because there's already a 7 here, so this is 6. Therefore, this is a 1. 1 plus 5 equals 6. This is making a mockery of me, it really is. Right. Okay, so do we do this bit now? We've got 2, 4, 8, and 9 to put into there. And we know we're adding 5 to this one. So we're not adding 5 to 2. That will not work, because I can't make those two squares add up to 7. Oh, in fact, I'm not adding 5 to 4 either, because I can't make those two add up to 9 either. So I'm either adding 5 to 8, in which case those have to add to 13 and would be a 4, 9 pair, or I'm adding 5 to 9, these would add up to 14, and oh, we can't use 6, 8. So in fact, this circle I think is forced. That's 8. Those two squares are going to be a 4, 9 pair. That gives us this digit as a 2. This 4 is giving us a 4 here and a 9 here. And we pause for breath and have another think to ourselves. This is so, it's just, I mean, it's classic zetamath. I mean, that is just about as high a compliment as you can pay a puzzle. It's just very, very clever stuff, and incredibly original as well. Right, so if this is a 5, that's adding up to 9. If this is a 6, this is adding up to 10. That is not helpful, is it? It's similar on this side. Well, if that was 5 and 2 adding up to 7, couldn't be 3, 4. It could be 1, 6 or 2, 5. Don't know if that's where we're meant to look next. That doesn't look very promising, I have to say. 4, look, has to be down in a domino in box 7. Not actually getting much more out of that. These ones, are these in some way restricted? Whatever this is, I add it to 8, and these ones add up to that. So if this was a minimal digit, these would have to add up to 9. Couldn't use a 4, so there'd be 1, 2, 6, or 1, 3, 5, all of which looks possible. And this, of course, doesn't have to be a 1, it could be a much bigger digit. No, okay, I'm a bit struggling here. It works the same way on that side. What on earth is it I'm meant to look at next? 4 here. So that's got to be added to this digit to give this dominoes value. No. These two add up to 15, don't they? Is that doing something to those squares? Don't think so. Oh, well, yeah, it's a little bit interesting actually. Those two squares, whatever they add up to, I have to add those two squares to that, and that gives me the value of that foursome there. So that foursome is adding up to at least 18. Well, that's not useful at all. Then these ones... Oh, no, I see. Oh, good grief. Right, okay, I've been coming at this backwards, I think. I think I'm not meant to look at these. I think I'm meant to look at these two, because I can get the value of these two, of course. Oh, right. As it seems so often today, I've been a bit nonplussed by this one. Right, but look, we can use the secret on box 8. The secret, of course, being that the outline cells add to 45. Those three squares add up to 21. So these squares add up to 24. But we know that these squares here, let's highlight them, are the sum of that plus that, and then that plus that again. So this is counted twice in that. So 2 lots of 8 is 16, plus 1 each of these. So these two have to add up to 8. That's really annoying, actually, because that we can't actually rule anything out there. These two add up to 8. Let's just put the options in. 1, 7, 2, 6, 3, 5. That can't be 5. Oh, we've got good lift levels of pencil marking here. But now we know the value of these cells, don't we? Because if these add up to 8 and these add up to, what was it, 15, eight and 15 is 23, so these add up to 23. I'm going to colour those a different colour. I'm trying to keep track of this. So these add up to 23. 23 and 4 is 27. Those two add up to 8. It's 35. These two squares add up to 10 to make row 7 add up to the right number. Oh, that's ridiculous. Oh my goodness me. That is absolutely beautiful. Wow. So actually, these two squares are a 3 and a 7 because they can't be 4, 6, 1, 9 or 2, 8. We know these two squares add up to 10, and they can't be the other 3 versions of 10 in 2 cells. That's really very, very lovely. So let's get rid of those 5s there. This is a 3, 7 pair. Okay. Oh, oh, and it's even more lovely because that rules out everything from these two squares. Well, not everything, but it rules out 1, 7, so we can get rid of that, and it rules out 3, 5, so we can get rid of 3 here and 5 here, and we end up with a 2, 6 pair. Wow. Which is beautiful. It really is absolutely beautiful. But the thing I'm a bit concerned about is that I don't think it's actually... Oh, there must be a 5 on this line now. Because I know one of these two squares is a 5. So there's a 5 on this line. It doesn't feel like we've got enough of a restriction in row 7. Hopefully I'm wrong about that, but my instinct tells me that there isn't enough to go on. So these two squares, oh, if they were an, oh, okay, they can't be 8 and 9, can they? That's 17. These two are going to be too difficult. You can't make those two squares add up to 17. So there's definitely a 1 in one of these squares, which means there's no 1 on the left-hand side of the grid. So this is either 1, 8 or 1, 9. Oh, I see. Oh, so this is never a 6. This puzzle is just genius, isn't it? You can't put 6 in here because 6 plus 6 is 12, and you can't make these two squares add up to 12 if one of them is a 1. So this is a 2, this is a 6. And now these two have to add up to either 9 or 10. 9 or 10. So this is either a 7 or an 8. Oh, if it's either a 7 or an 8, its partner is either a 7 or an 8, because we know that together those add up to 15. Good grief. Okay. So now, can we get this digit? No. Because we're either going to have 6 plus 7 equals 13 with 5 and 8 here, or 6 plus 8 equals 14 with 5 and 9 here. Oh, but this 2 is giving me that digit. Maybe that's how we make progress. 3 is in one of those two cells. So 3 is in one of these 3 cells. Oh, I see. These are a 3-4 pair. So if these are a 3-4 pair, 4 is in this domino. And this domino adds up to 10 or 11, which doesn't feel like a very propitious total, I have to say. 2 7s and 8s. So these squares here are 2s, 7s and 8s. That one is not 8. I don't think there's a triple in this column, but I might be wrong. I don't think there's a triple in that column either. I can't see one, I really can't. Okay. So, what on earth do we do next? I've not got a clue. It's so strange doing a puzzle like this because you feel completely reset in terms of puzzle experience. I feel almost like a puzzle experience is unhelpful because it's making me look at all the wrong things over and over again. Is there... I haven't got a clue how to do this. Oh, I know what it could be. If those add up to 10, how difficult is that to achieve here? Similarly, 14 here is probably quite difficult to achieve. If that's 10, which it is, and that's 7, this has to be a 1-2 pair. Is there a reason that doesn't work? I'd be repeating the 2, but we know that's okay. If this is a 3, on the other hand, these two squares have to add up to 7, but they could be 1-6 or 2-5. I do actually feel like we're very close to a restriction in these cells. Feels quite difficult. What about 14 on the other side? Is there some reason that one of those becomes difficult? 6 in box 4? No, I don't think that's where we need to look. Okay, so I now really do feel very stuck. What is it that we're missing about the structure of this? Where can we find more joy? If this was 11, is that difficult? 2, 9, 3, 8, 4, 7. It would have to be a 5, 6 pair. Ah, yes, okay. That's really tricky to see, and there might be a simpler way of doing this, but if we look at this digit, I don't think this can be a 3. Because if this is adding up to 11, which it would now have to, because these add up to 14, 14 minus 3 is 11, I don't think there is a way of doing that. 2, 9, 3, 8, 4, 7. If this is a 5, 6 pair, that digit's not filled. So I think this is 7. Oh, where would it let me put it in? That's a 7, that's a 3, that's a 4, that's a 3, that's a 4, that's a 1. Nice. And this 1 is beautiful because that's putting a 1 here. And we know it must accompany a 6 because we need to make this add up to the right number. So that becomes the 5. This needs to add up to 10, so this becomes a 2. That places a 2 here. Good grief. And we are actually doing quite well. Now actually, now I know those two squares add up to 8, so this is an 8. That's a 7. I've just realised I knew that already. I've got to go back and look at that. Hang on. This shows how absolutely wonderfully inept I am at this puzzle. Look, I deduced this digit. I could have just written this digit in as an 8. Oh, but I don't think it did anything, did it? I'm not sure whether it did anything. It might have done something profound, but I bet you've all been shouting at me about that digit. It's just because I'm just totally not used to the rules, he says. Now, well, that's good, isn't it? Because now what do we know? We know a lot more about row 4 than we did before. We've basically done, hang on, we can carry on. That's got to be a 5, and that's got to be a 6. So maybe these dominoes are where we're meant to look. This has to add up to 9. It's not 4, 5, it's not 3, 6. It's either 1, 8, which would have to be this way round, or 2, 7, which would have to be this way round. So that's a little bit restricted. This side, we've got something similar going on. Look, we need 9 again here. We can't have 2, 7. We can't have 3, 6. We can't have 4, 5. This is 1, 8, and there's a 1 there. Right, so 1, 8 go in. That fixes the 2, 7 on this side of the grid. And we're not that far from having used all of our lines. Which would reduce it to a Sudoku problem of all things. Okay. 2 has to be up there. 7? Oh, 7 can be in all 3 positions in box 3. So is it... I've got no idea where I'm meant to be looking here. I really don't. Is there some restriction I'm not understanding? Or is it Sudoku that I'm... 9 is a bit restricted, I've just noticed in this column, and maybe that one as well. 9 can't go here, here, or here. 9 is in one of 2 places. If 9 is on the line, they would be 12, so this would have to be a 1. That might be possible. Oh, also... this is lovely. I see. I've done it. 8. Where does 8 go in column 3? Not there, not there, not here. Remember there's a 7, 8 pair already in the row. And not here. This is an 8. Oh, this is good. Yeah, this is good. Right, now this is a 5, 9 pair. 5 and 9 add to 14. That gives us an 8 here. A 7 here. These 2 squares now don't include a 9, so this is a 1, 8 pair. Oh, okay, and that adds up to 2 plus 7, which makes sense according to the rules of arithmetic. So... we know those add up. We know this domino adds up to 10 now because we've got 13 here minus 3. So it's not 2, 8, 3, 7 or 4, 6. This is 1, 9, which means these 2 squares are 2 and 6. And let's check that adds up. That's 12, 5 and 7 do add up to 12. There's a 2 here. So this is 2, this is 6, this is 2. What about this column then? Where we need 5, 7 and 9. So this is 5 or 7. This is 5 or 7. This is 9. Now that might... does that do the 9s in column 3 as well? 9 can't go here, here, or here. Oh, I see. And I could have ruled this one out once I knew this was 5 and 9 as well. So that's 9. That's 1. this is a 1-4 pair by the power of Sudoku. This square here is a 5 because there's a 7 there. That's a 7 at the top of the grid. These two squares are an 8-9 pair to complete the box. These two squares are a 5-6 pair to complete that box. 5s, where do 5s go in column 3 now? Not there, not there, only there. So this column now needs a 1 and a 3. Well, that's going to be the 3, that's going to be the 1. That does my 1 and my 6 now. These two squares here are a 2 and a 7. Okay, I don't think that is resolved, although it might be, once we think about this domino, 12 is what we need. Yes, how do we make this domino add up to 12? There's only one way. That's 7, that's 5, that's 6, that's 2. Can we do the same on this side where we need... Yeah, we can. These two have to add up to 10. There's only one way that will work. 1, 9, 8, 4. 1, 8 go into the grid. 5 and 9 over here, and now I think we have reduced it to a Sudoku problem. These squares, that's a 7 by Sudoku. This is a 6, that's a 3. Those two squares there are 4 and 7, which we can also do. These are a 2-3 pair, which we can do. Oh, this is just lovely, isn't it? 5 and 9 here. Yeah, that is resolved. 5 and 9. 3, 4 and 6. Don't know if that's quite done. It might be, but I'm not immediately seeing how to do it. That's not 4. What about those squares then? They are 3, 6 and 8. There we go. So that's a 6. That's an 8. That's a 3. That's a 6. That's a 4. That's a 3. And we should be left with 1, 4 and 9, which places 1 here, 4 here, 9 here. Click, tick. Yes, absolutely lovely. That was really cool. It made a complete monkey out of me, and I apologise for that. But I did get, well, what was I really pleased with getting? I think I understood this once I thought about it relatively quickly, and the effect it had on these digits. So it's really, really beautiful that you could sort of back into the value of these two squares. And the fact that that's built into a solve, and it happens after a lot of other logic. So zetamath has basically, I think this was the start. That seemed very, very clear. The fact that this is a 5 is lovely, and the way that the sort of logic worked upwards. But then to build this bottom stuff in so that it works so elegantly without ruining it with what you've put in the top is a mark of a very, very classy setter indeed. Really enjoyed it. I hope you did too. Let me know in the comments. You know I enjoy them, especially when they're kind. And we'll be back later with more videos, and Bubba is you. See you later on Cracking the Cryptic.